Hello everyone, this video's topic is diamond silicon vacancy, and here I will give a presentation to introduce the paper Single Photon Switching and Entanglement of Solid-State Qubits in an Integrated Nanophotonic System, which is published in 2016. I hope my interpretation will help you to have a general understanding of the frontier work of this paper. Okay, let's get started. First, I want to explain why I chose this topic. We have well understanding of MV Center after half semester's learning, and now we are familiar with the level structures and its application in quantum engineering. Although it has many advantages as the paper said, but also some flaws are mentioned. I want to do a transverse study to see what are the common properties of this type of materials and in what else application can this structure in diamond be used. This paper is about the technologies and applications based on silicon vacancy center. Now let's talk about the motivation and the critical assessment of this paper. We need to know that an integrated platform of scalable quantum nanophotonics is very important for applications in quantum science, such as quantum computing, quantum chips, and quantum communications. And efficient interfaces between photons and quantum emitters is the key for the integrated platform of scalable quantum nanophotonics. However, there are great challenges to realize such an integrated quantum platform in solid-state systems, and this work presented an architecture by integrating silicon vacancy color centers in diamond nanophotonic devices to overcome these challenges. What challenges need to be overcome? I think there is a big challenge in overall goal and some difficulties in implementation. The outstanding challenge is weak interactions between single photons and individual quantum emitters in solid-state systems. That means how to realize strong coupling between single photon and individual emitters for constructing an integrated quantum devices. And the difficulty includes how to suppress the effect of destroying quantum coherence of the coupled qubit systems, such as inhomogeneous distribution, rapid decoherence, and significant spectral diffusion in optical transitions. Also, the random positions of the quantum emitters in solid-state systems, which makes the realization of scalable devices with multiple emitters difficult. Then, we were curious about what are the advantages of the diamond integrated platform with silicon vacancy centers. According to the paper, its advantages are very attractive. First, it is facilitated to realize the strong coupling between single photons and the silicon vacancy centers in diamond photonic crystal cavity. What's more, the positions of the silicon vacancy centers can be precisely implanted into diamond waveguide or photonics crystal cavities. Also, the effect of inhomogeneous distribution, rapid decoherence, and significant spectral diffusion in optical transition can be greatly suppressed due to the inversion symmetry of the silicon vacancy center, which results in the nearly lifetime broadened line-wise in optical transition spectra. Now we can go to the second part, technical assessment, including the main results and which technologies and methods are used in the experiment in this paper. The authors explain this result separately under each subtitles to show the method and technology details. The fabrication process and experiment involve lots of optics knowledge, which I learned in my undergraduate, and I know it's not wise to explain each concept and principle that are mentioned. I will try to simplify the details and focus on the main outlines. The first question is, how they fabricate a diamond integrated platform with silicon vacuum centers? Here are the keys. Technique 1. The angled reactive ion etching is applied to fabricate a one-dimensional waveguide and photonic crystal cavities. Technique 2. The focused silicon ion beam implantation is applied to deterministically position at the center of each cavity for optimal coupling between an individual silicon vacuum center and the cavity mode. Technique 3. The annealing processing at 1200 Celsius degree in vacuum is utilized to form the silicon vacuum centers and mitigate crystal damage. Figure 1 shows positioning and strong coupling of silicon vacuum centers with diamond cavities. What can the diamond integrated platform with silicon vacuum centers do? Here are some functions of it. Function 1 is it has the ability to realize the quantum optical switch between the transmission and fluorescence emission at single photon level based on a single silicon vacuum center in diamond cavities. We can see they made an all-optical switch with memory by optically controlling the metastable opto state of a single silicon vacuum in Figure 2. The energy level structure and preparation method of initial state is very similar to MV center. Use gate pause to choose state C or state U as the initial state. In Figure 2C, we see that when state U is the initial state, the probe pulse will have high transmission rate and low fluorescence rate. If the initial state is state C, is the opposite, and this is the switch. They also did an experiment to verify optical switching at the single photon level by using photon correlation measurement, as shown in Figure 3. The key point is the value of G2, the second order correlation function in Figure 2b. If we don't understand this function, it doesn't matter. We only need to know that it can be used to determine whether the scattered photons are single photon emission. In general, when this value is less than 0.5, we can assume that it is at single photon level. The result in this paper is 0.15, so it is a good result. Of course, the ideal single photon corresponds to G2 equals to 0. The function 2 is that it has the ability to implement the tunable single photon source by using Raman transition. Although in this system, the spectrum line-wise in optical transition was suppressed by some of the previous techniques, some uncertainties in the fabrication process still result in a relatively broad bitwise of fluorescence spectrum. So how to solve this problem? The answer is to use Raman transition technique. From the Figure 4b and Figure 4c, we can see the virtual state that has a data detuning from resonance frequency, which is the magical place of Raman transition. The line lines of Raman peak is narrower than that of the fluorescence peak. Moreover, the Raman photon frequency and the spectrum line-wise can be controlled by controlling the Raman laser light intensity, which means the spectrally tunable single photons are realized by using Raman transitions. Function 3 is that it has the ability to achieve the entanglement between two silicon vacancy centers in a diamond nanophotonic waveguide. Figure 5 shows such an entanglement by utilizing an efficient probabilistic entanglement generation scheme based on detection of indistinguishable photons from Raman scattering of two silicon vacancy centers. Figure 5D gives the second-order correlation functions from single silicon vacancy center and two silicon vacancy centers, in which the blue and red lines respectively correspond to the classical mixture state and the entangled state of the two silicon vacancy centers after detection of a distinguishable photon. At last, what can we do to improve these technologies? The first thing is increasing the coherent time by operating at low temperatures or engineering the photonic density of states to suppress photon relaxation processes. The second is improving nanophotonic designs using slow light waveguides and cavities with higher Q ratios. Furthermore, the efficient fiber diamond waveguide coupling for improving the efficiency, even exceeding 95%. And for applications, first, their work shows possibilities for realizing large-scale systems involving multiple emitters strongly interacting via photons. And because of the large cavity bandwidth, more than 10 coupled emitters can be addressed independently in a single cavity to form complex quantum nodes that efficiently couple to a fiber network. So such a system paved the way for the realization of integrated quantum networks with applications such as long-distance quantum communication. Okay, that's all. Thank you.